So this is also a band mode shape. So this is 132 hertz, and here this is 135 hertz. Maybe, see, what is the reason there is a discrepancy between the data, what we get from the data, and what we get from the model, mathematical model. What could be the reasons? What are the reasons? One reason could be how we set up the experiment and how we collected the data, right? When we put the shakers in there, maybe it has affected its natural frequency, right? Or could be the other reason when we selected all the bands or the other, we narrowed down our mode shapes here, like what FRFs to consider. Maybe we made some engineering judgment here. We have to look at.
Could your mesh, changing the mesh, how fine your mesh is?
Yeah, we can go. Yeah, we can, based on the how many nodes we got for this, we got only 15 nodes. Say we have more nodes. So, for example, in the band selection page, we selected from 80 hertz to 600 hertz. Say we go higher hertz, we won't be seeing much results in terms of the much difference in the results in terms of the mode shape.
Okay.
Because we don't have enough nodes to generate that kind of vibration, higher vibration.
But in SolidWorks, you've got a lot more nodes.
Yes, in SolidWorks, because its computer is generating the interpolating the data between the nodes, and we told it you can go higher frequency in SolidWorks. But here, yeah, it's experimental data, so that's why it's not as smooth in SolidWorks. Basically, it's allowing us, it's giving us another type of information for our selection process, right? You can see small letters here all over the place in the plot. S, O. When it says O, that means it's not a good location for natural frequency. When it says S, stable, means it could be a probable location for natural frequency. So what it's doing is doing some mathematical analysis on the data. Simply put, it's doing some polynomial fit of degree up to 32. As you can see on the left hand side, right hand side. So it's doing some polynomial fit up to 32. For each polynomial fit, say let's say 12, it's giving us some indicators like S, F, something. S means a stable, and we are interested in the stable. So we select a stable ones. So now on this page, we're going to scan the software where the mathematical fitting of the FRFs looks like, whether there is a correlation or not. So these green and blue, red and green plots are the mathematical and fitting of FRFs. Ideal mathematical fitting, and these blue lines are the mode shapes we calculated from the data, whether there is a correlation between the two. We see here for this particular natural frequency there is no peak. So the correlation for that, the correlation for this one is not 1%, it's less.
Oh, so it's like
Are you guys from the dynamics?
oh,
You should be able to download the file, the project file for the Siemens test lab. Have you guys downloaded that into your UPS OneDrive?
okay.
Yeah, I know, it's headache. You can do it from your UPS email too. You don't need to have workspace. Just download the Siemens, yeah, any computer, you go to UPS email, and then you can go to the OneDrive icon from the UPS email, and then you can upload it there, and then you should be able to see your file in the Siemens test lab. Going to be slow. This happened yesterday too. Were you here today? Oh, yesterday? No. published. You got an announcement from Ben, right? In the ED. There's a link there to take you to the lab materials. Yeah. Yeah, it's not. No,
Maybe I should.
there's a little.
Oh, lovely. Yeah. I'm gonna try that. We'll have to
Yes, this one.
Oh, it's on camera.
Yeah, it should be there. I need to SolidWorks. Here's some simulations to find the mode shapes and natural frequencies. And then we're gonna, in the next exercise, we're gonna do the Siemens test, right? It has to do with the data analysis, so some data we got from the experimental rig. And we're gonna see same kind of mode shape and natural frequencies. This kind of verification, checking both the simulation and the data, how they correlate to one another. The simulation is to help us predict the experimental data. This kind of judgment we use as an engineer. Always we do simulation to understand, predict or design an experiment. Right? So Siemens tells that model analysis is basically a data analysis software. Just you can think of an advanced version of the Excel, right? But specific to the model analysis. So, try SolidWorks here. Now, any questions? Yes. No questions? All good? You're doing good. Yeah. So basically, here, how many natural frequencies we have on at the location? What the software telling us? One natural frequency, because the FRF sum is there's one peak, and the green there is say one opposite peak, right? In the deep band.
Sorry, so like they cross each other.
Doesn't need to be. So we can turn off the sum. We can turn off the sum. Suppose there's no red plot. We look at the mode indicator functions only. There are two functions. One is green, one is blue. What's happening with the green one? It's coming down. That means there is one natural frequency. What's happening with the orange? It's not coming down as much. That means there is no natural frequency. So what the mode indication function is telling us is a different way for us to look at where the natural frequencies are. So this software is allowing us to find the natural frequencies by looking at mode indicator functions instead of just looking at the FRF space. So that's what it's doing on this page, time end off. So we are in the band page. If you look, we are in the band page now on the top. So it's allowing us to select, narrow down our analysis band. Let's say we want to carry out the analysis within, starting with 80, you can select here, from here, and go up to 600 or 700. So based on our observance of the data, how the data it looks like, so what the software is telling us is giving us some plots from the data. So it generated some mode indicator functions from the data so that we can refine our selection process. We can select the band, say starting with 84 and going up to, so we narrow down our analysis select region, right? And then we go to the next page. It's allowing us to do more refinements to our data. So we go to the stabilization page. On this stabilization page, what we're seeing here, are you guys from everyone from today's lab or from yesterday's? Today? It works. So let's see. We go here, create a new project, and we can choose part as our project, and OK. And the new project blank space comes up, and here we can go to start to work on the part. So we're gonna create the part first by drawing a sketch of the part, 2D sketch. So you can go to the sketch tab and then click on the sketch, and then it lets you select the plane on which plane you want to draw your sketch. So we're gonna draw on the front plane, and then we're gonna use a rectangular shape, draw a rectangular shape, and then we can put the dimension now. Press escape to come out, and then click on the smart dimension, and we can click on any of these edges to set the dimension. Let's say we want to set the dimension for this edge, and this is gonna be, we just look at the lab handout. So this is gonna be 530, and just press enter and then click on this edge, and this is gonna be 320. So we set the dimension, but it still doesn't have the thickness. We come out of the sketch, just click on exit sketch. Now we have that sketch. You can rotate it by clicking on the middle mouse button or dragging. See, there's no thickness in there. And then we go to the feature to add the thickness. And we click on the extruded principles while selecting the sketch from the project tree. Then it will allow us to add the thickness. You can see. Now we type in the thickness here. So we're going to give it a 23 millimeter thickness, and click OK here. And now that we have the part ready, so this is the part. This is the same kind of part we're designing we just designed in SolidWorks. Very simplistic, a mathematical part. Not so we created in SolidWorks for the simulation purposes. Now we want to carry out a simulation on this part. To do that, we have to make sure we have simulation add-on is activated. We can find the simulation add-on here. Just click in here, options, add-ins, and make sure you have this simulation, SolidWorks simulation checked. And when you have that checked, you can find the simulation tab here. And then we go to new study. So we're going to carry a new study for simulation, and we're going to do a frequency analysis. Only the frequency is checked and everything else unchecked. Click OK. Now we are in the frequency analysis page. You can see our part. Now we can now see our part here. First thing we want to do, we want to apply a material to this part. So right click on the part and apply edit material. And it's going to bring up this window. Dialog box.
Sorry,
Yeah.
I'm a bit lost. How did you get to this simulation page?
It's on here in the tab. If you're on the top,
Yeah.
you can select different tabs. Now we are in the simulation. So when you're in the simulation, click on new study.
Right.
Have you done that?
Yeah, I'm following.
And then you have to select the frequency from the list on the left. Panel.
There we go.
Click OK.
Cool.
All good.
Thank you.
Yes. So this is our part. This is a simulation tree. For the simulation, we will have a standard procedure like here. We have our part, and then we have any connections, we have any fixtures, we have any external loads, and we have the mesh. For this analysis, we don't have any external loads, so we don't have to do anything like with this. We don't have any fixture, just like we have the experimental equipment. It's like a free body. There is no fixture, there is no load, there is no connection to the part. So we just apply the material, right click on the part, click apply material. And here we can apply, search for the material we're interested. So what I think we need acrylic. If you search here acrylic, it will show up here acrylic. And select acrylic and apply. And it's going to apply the material into our part. As you can see, our part looks okay. But this is the first step. Then the next step, we create a mesh. So a mesh is something before with simulation, you have to discretize the part into smaller elements. This is for the simulation purposes. So we're gonna right click on the mesh and the create mesh. So basically we're breaking down the part into a smaller parts for the simulation purposes. And here we can choose the size of the elements for our part. We can choose fine or we can choose coarse. To exactly know the size dimension of the elements, you can click in here and it will tell you here in this box what kind of dimensions for the elements, right? So we choose, since we know the thickness of this plate is 23, we want to fit 2 elements into the thickness. So let's say we want to set the element size 1150. So now we can fit 2 elements into this thickness. So it's going to produce a better simulation results than having just one element into the thickness. Obviously, the more elements you have, the better results gonna be, the simulation results. But for this exercise, we just keep it too simple. Just keep it 2. And then that's all. Just check here, okay, and it's gonna generate the mesh or elements for the part. So all these elements now you can see in the thickness we have roughly 2 elements here, and that's all. So the part is ready to be simulated for the frequency study. So before we do the study, because this is a uniform plate, so let's say along this axis, x-axis, we can have infinite number of natural frequencies. Right? It's up to us, our infinite number of mode shapes. But in the study, we can tell it how many we expect. So we can go here and study properties and number of frequencies, natural frequencies we would like to get from this simulation. Let's say 12. We want to get 12 for this study. But actually, out of these 12 natural frequencies, the actual natural mode shapes we'll get is 6. I'll tell you later why we get 6, not 12. But we select 12 here, we can then OK, and this is now ready to go. Now we click on the run this study. This is gonna take some time and it's doing the calculations for the FEI. And it's going to produce the results in the simulation tree, project tree. So it's produced the results here, as we can see. Yeah.
Why the material? Like I'll go apply the same why little side material.
Not apply?
So if I get the apply material, like that's even what I'm doing. I go down.
I have to do with that too. Doing it in slow is easy.
It doesn't know which part to apply. Yeah. You're doing wrong. This is the site for the workspace. This will not be using that. Just go to GTS workspace and it will tell you the exact address of this site. Then you punch in the next step, you put in your login ID. But now you have to find the address from the GTS workspace. Getting a started page, you have to go to the getting a started page, it will tell you for the busy. No need to close that.
It's like a lecture, right?
Yeah. Movement we go for. And you can choose the frames, speed, just a stop first, and you can. 10 minimum frames and then 100 speed. It's a bit slow. Yeah, we're doing SolidWorks. We have to fire up here. We have, yeah, exactly. We have to fire up SolidWorks from Workspace. Yeah, good, great. So the first 6 results we get here in SolidWorks actually rigid body natural frequencies. What do we mean by rigid body? Basically, the entire body is not deformed, it's just the whole body is moving. So that kind of natural frequency. Like for the first one, as you can see, the wireframe, you see the wireframe is the natural position, and then it's moved on the left. So it's vibrating along that axis. That's one natural frequency, but we are not interested in rigid body natural frequencies. So that's why we should go to number 7, which is the first natural frequency with the deformation. As you can see, and you can find the natural frequency here, highlighted here, moon shape belt. So the first natural frequency we get from this particular experiment, 131 hertz, something hertz. And next is 132. You can double click on each of the moon shape produced, 297. So you can correlate this later. We're gonna correlate this later. The Siemens test lab data, experimental data. So, and then you can see how each of the moon shape looks like by dragging, and you can see the color coding of the shape. So basically, it's as simple as that. And then go to the plot, animate. You can animate each of the moon shape here. You can set the number of frames for animation, the speed for the animation. We set it to 100 for our purpose. Let's say play, and it's gonna play the moon shape. And when we observing this moon shape, we're gonna observe the same kind of moon shape in the data analysis part of the Siemens test lab. So you can save this as AVI file for your future reference. You can save it from here somewhere. I would recommend save it to your OneDrive, or you can just take a snapshot of your project. See all your moon shape here. So that's all. I think there's no question with this. This is very straightforward. We go to the Siemens test lab now. So in the workspace, you have to open model analysis. You can find it under Siemens folder.
Just swallowing me out.
Really?
Yeah. I think this is
So many people using it, like one reason.
Yeah, because it's like even if I drop it, like because I have to like for a thing, if you can't just drop it,
It happens from time to time.
and they haven't actually,
It's an idea.
so they haven't actually do it yet, but they said that they'll do it this month. But even if I drop it, I'll just finish it off this semester,
Have you tried?
and like first week next semester I'll just submit it.
That's the real question.
Why don't you join our
There's nothing to do.
for 3 months? Just sit in class.
There's no task for it.
You guys can have the same. Yeah. Now we move on to the next part, please. Yeah. Bigger is in a Windows settings, I suppose. You have to go to the Windows. You know how to do it. But we're moving on to the next part now. Siemens test lab. Later on, I also go on to. You can come back always to this part. And here, we choose the highest. but you have to restart the project.
Oh,
Maybe just minimize this for the time being. We go to the Siemens test, otherwise you can't, you will be lost.
And then I was like 4 weeks into accepting robotics
Sorry.
Oh, no,
Yeah, you guys can work together. Yeah.
how do you get the simulation? Like you had?
Simulation, we already in the
Yeah,
simulation.
you were already in
We applied and we like.
Yeah, I already did it. Actually, yeah.
And then we created the mesh, I suppose.
Yeah.
It's one mesh, but two mesh. Anyway, I think too much is because we can always
I
say
one
mesh.
side.
Even, so this is the element size. Anyway, it will generate the results here. You will see the more
Okay.
shapes. Now, I think better to we move on to the next part. Siemens Test Lab. So in the Siemens Test Lab, we open the project file, LMS file that we find. We go here, open project, and for me, I saved in my own folder. Let's try to find. So basically, the project is flat plate, 15 shaker. And click OK on this. Should be okay. And it will take a while to load up the project. Just like the Excel project, Excel file, it starts. So you can save the data in a project. That's what we are doing here, Siemens Test Lab. So this is a project. So in the project, you will find here different buttons under. So these are for navigating us through the individual steps we need to follow to do an analysis, model analysis from the data. So the Siemens Test Lab has its own workflow. So it has given us a workflow like we start with the documentation, we go navigator and do model data selection and the time end off, and then we can do model synthesis. We can do after that we do model validation. So each of these pages you can click and see and modify things, and then at the end we generate some results. And on the way there, we can change things and experiment with things. Basically, that's what. So this is, you can see for our project there is empty documentation, there is not much else to do, but if you have your own project, suppose in the Siemens Test Lab, you gather some data, you can attach any documentation in your project on this page, in the first documentation page, and then we go to the next page, the navigator page. Here, it's kind of giving us an overview of the project. Like we can explore our project, how it looks like. So in our project, flat plate project, we have a shaker test experiment, data collected. In the shaker test data collection, we got 30 FRFs data, frequency response function data. And also inside the shaker test, we have, yes,
Oh, so are we supposed to save the SolidWorks file in a certain way so we can access it? So are we supposed to save the SolidWorks file?
yes, you save it because we're going to compare it, right?
Oh, okay, because I opened the SimCenter test lab and it's not recognizing where I saved the SolidWorks file. So I'm wondering if I saved it as the wrong file.
Oh, you know what?
I just saved it as a SolidWorks.
Yeah, it should be able to solve the
So you put a specific folder, we change it to.
Yeah, that's the solid file. But in Siemens Test Lab, we are not using SolidWorks file. We are using a different file card, which is called LMS file.
puzzle just in this straight forward.
Not, it's in the your canvas. It's posted in your canvas. There is a Siemens Test Lab project file, LMS file. You have to open the project just like I opened. It's called Flat Plate 15 Shaker. In fact, yeah. Open that project in your. First thing, maybe you should upload that project into your UTS OneDrive, and then you should go have a look in your Siemens Test Lab. Have you started Siemens Test Lab?
We're trying to figure out if the polls are the same.
Yeah, from SolidWorks or from Zoom, I'm actually sure.
Oh, really? You have to set up. Can I use mouse?
It's maybe if it's a part, maybe it's a mistake.
OneDrive, you have to synchronize.
Oh, maybe that's why.
Yeah, you have to make sure it's
I already opened it. That's the one to shake it.
But it's okay. I think later on it will be synced. But yeah, you can. As long as it's showing here, it will be synced later. So you can save it here. It should be doing it later. So that's what we're seeing here. In the Siemens Test Lab, in the navigator page, we see our project. In our project, like shown here, 2 shaker tests. We have 30 FRF data we collected from the experimental setup, as in your lab handout. So these FRFs, you can plot it in here on the right panel. You can click on this to draw a plot, and then drag and drop your FRFs to see how it looks like, each of the FRFs. So basically we are kind of making sure our data looks okay in Siemens Test Lab before we do an analysis. And under our project, we also see we have a post-processing here, processing folder. Basically, it contains the model analysis data we did before. So in this project file, someone already did some analysis before, and it's called, they saved it as a processing. So we're gonna do our own processing, we're gonna save it here as well. You can have multiple results saved in the same project analysis. Then you have geometry here, where it's showing, okay, for our project there is one geometry node. So it's shown here, the name of the geometry node. You can view the geometry node by selecting the quad here, quad geometry. So it allows us to draw the geometry as a quad, as quads, and then drag and drop this geometry node into the view, and we should be able to see how the geometry looks like. So that's how the experimental setup looked like in terms of the data. Like that's how the data is viewed inside the Siemens Test Lab. So geometry is created like that. You can right click here and to add more information into the view. Say we want to add the node names. So say these are the nodes we collected from our experiment. On these nodes we collected FRFs. On each node we collected FRFs. So 15 nodes we collected 30 FRFs. So the naming of each node you can see here, 2.1, 2.2, 2.3 and 2.4 in that order, 2.5. Basically when they are collecting the data, they follow that path. This path, this path. So that's how it is shown here. So and then once we are happy with this, we can do one more thing. We can go and add ints and then activate the geometry page. What it allows us to modify the shape of the experiment from the nodes. So you can see here the geometry tab open here now because we activated it from the add-ins. add-ins page, dialog box. We can move this to after the navigator page by going into workbook configuration and geometry, move it up to next to the navigator. Okay, and you can see it's moved here now next to the navigator. And when we click on the geometry page, now it's giving us more information. Okay, on this geometry, we have sub pages or tabs inside the geometry page. We have component. We have only one component. The entire plate is one component, and it doesn't have any kind of so everything is zero. Its coordinate is zero. Basically, the entire plate is coordinated at zero, and we can choose the coordinate system for the calculation. You can choose from here Cartesian, cylindrical. Basically, but for this experiment, we keep everything as default Cartesian. There's no rotation to the plate, so it's all zero. Then we can go to the nodes page to see how each of the 15 nodes looks like the coordinates. So you can see the coordinates, x, y, z coordinates of each of the nodes. Let's say here name, we add the name. So 15 nodes out of 15 nodes, and you can check the full name of each node. We've got 15 nodes and the x, y, z coordinate of each node. So you see, suppose you collected the data and you see the nodes are not located correctly, you can adjust them here on this page. So before you do model analysis, the mode shape analysis, you have to make sure, okay, this is how my setup looks like. But for this, it's all correctly entered before for us in this project. So that's all. Then we can go to the model data selection page. So in this page, basically, out of 15 nodes or 30 FRFs from 2 reference shakers, you can see here 15 responses from each shaker and 2 reference points. 2 shakers we use for the experiment. So each shaker maybe was located differently at different nodes. Say first shaker on this node and then second shaker on this node, and then while the first shaker is moving on to the different nodes. That's how the data is collected. We have 30 FRFs out of 2 reference shakers. So here we can see the sum. Now in the plot we see the sum of all the FRFs. This is the sum of all the FRFs. From the sum we can see the peaks. So these peaks corresponding to the natural frequencies as we can imagine. And we can add a cursor here by right clicking X cursor, and we can drag our cursor to the location to see. So this is telling us 133 something, but Hertz, right? But in SolidWorks we saw similar Hertz for first natural frequency, right? And the second natural frequency, maybe this one. But this is all the sum of all the FRFs, like summation of all these FRFs you can select. But to see each of the individual FRFs into the plot, you can uncheck this one, tick this one box, selected FRFs, then it will show you the one you're selecting. Only the selected nodes FRFs is shown now here. And we can also check multiple, you can select multiple to view multiple FRFs into the view. So this is allowing us to select the FRFs we want to take into consideration for the analysis. So for our purpose, we select everything. So let's say we found everything is good to go for analysis. We select everything from this panel. We want to select all the FRFs, and then we go to the next page, which is time and off. Is everything clear up to this point? No? A bit lost? Yeah.
I've opened up the
So in the next page, so basically this whole thing is allowing us to select the FRFs. Because we collected the FRFs from the experiment. That's what the project page is showing. In the first, in the navigator page, in the geometry, we verify how the geometry looks like from the nodes. And in the model data selection, we select the FRFs for our analysis. And that's what we do in the model selection. We select the FRFs. And we can also view the FRFs here for our purpose. Let's say we have a garbage FRFs. One of the FRFs is garbage. So we can omit that from our selection. Say the last one is not good after looking into here. So we omit that from the selection. Or we only want to do model analysis on these FRFs only. So we only select that one. For this experiment, we select everything. Right? Because we sure everything is good. All the data, all the efforts are good. So it's kind of like a selection process. We're refining our selection as we go through the project analysis workflow. We're refining our selection. So the software is allowing us to do further refinements into this page as well. In the time and off page, we do further refinements of our selection based on what the software is telling us. So the software is giving us 2 more plots of our data, all the FRFs data. So these green and blue plots are 2 more information, important information we can take into consideration for our analysis selection process. So here, these green and blue plots are called moon indicator function. You can see it's checked here, and also the other things checked here is the sum. Sum is the sum of the FRFs here as shown here. The red plot. So we know there is one natural frequency here, as we see the peak for the sum. There's another natural frequency here, another natural frequency here, so on. But in the first natural frequency, we see the green and blue plot both coming down together. Wherever they coming down, that means there is a natural frequency it's telling us. So what's going to happen in the first natural frequency here? How many natural frequencies do we have here? What do you think? Very close. Into the first page, the red plot is the sum of the FRFs. So the FRFs is not telling us much. It's just telling us one peak, right? One natural frequency into that location. But what the green and blue plot telling us, there are 2 natural frequencies. Because both of them coming down together. But they are very close together. As we saw in SolidWorks, one is 130 something and the one is 132 something. They are same. It's different terms here. So we can also call them poles. Poles. All clear after this point? Natural frequency should be look like. So there are 2 X closely together. So we select both. You can see the lines coming up. So we're telling the software these are the natural frequencies. There are so many S here, so we select that. S here, select that. So you can see the natural frequencies and moon shapes coming up here as we select. So we selected 7 by looking at this plot. So each of the natural frequencies is shown here, the one we selected, vertical lines, and also corresponding damping coefficient. Now, since we told the software these are the natural frequencies should be considered for generating the moon shapes from the data. Now we go to the shapes page. In the shape page, it's going to generate the shape for us based on what we have selected so far. Now we can give the result a name so that it saves. We can say processing shape twisting. Then we click on the calculate and see here is generated the shapes here for us based on what we have selected. So we can now click on each of the shape and we can click on the display and it's going to display the shape for us. Let's say this is mood shape 1 and as you can see, and then we can click on say mood shape 5 and display is going to display that shape for us. Now this is the main experiment we are doing with this software. Basically, from the data we are trying to generate the mood shape. To compare and contrast what we have found in the SolidWorks. SolidWorks is a simulation result. This is the result from the data we got. Now we're going to compare with the simulation. In the SolidWorks we got the first natural frequency we got. And then what the mood shape looks like. We compare both and see if there is any difference. Right. So the entire process is to know the difference, if there is any difference. Or have we made any wrong judgment into our this selection data refinement, right? So this is for mood shape and we go to SolidWorks. We look at the mood shape in SolidWorks as well. So this is 130 Hertz, 31 Hertz. And here this is 133 Hertz. It looks like this is a torsional mood shape. So on this axis there is not much motion. So this is a torsional mode shape, and then the second one is a band mode shape. And what's happening with SolidWorks in the second one?